Okay, so let's continue where we left off in the last class. So in the last class, we were trying to design classifiers or algorithms to find classifiers that maximize the margin. All right, so given a set of data points and a particular hyperplane classifier that correctly classifies all the points in the data set, the margin is the minimum distance from the data set to this particular hyperplane, right? And we want to make sure that that is as large as possible. And for this, we came up with the following hard SVM problem. Now, the problem of finding the max margin hyperplane can be posed as an optimization problem, wherein you maximize over all possible classifiers the minimum distance from the data set to the particular hyperplane defined by w comma b. Right, and we saw that this could be solved using the following hard SVM algorithm. And the advantage of using the hard SVM algorithm is that it's a nice convex optimization problem that we can solve. All right, and we showed that these two are essentially the solution to this optimization problem is the same as the solution to this particular optimization problem. Right. And towards the end of last class, I also talked about the Soft-SVM algorithm. But even before that, let's see why these are called support vectors. Why is the name support vector machine, right? And that essentially comes from the following analysis of the solutions to the optimization problem. So you can use the KKT conditions. After all, we have a convex optimization problem. So we have the hard SVM optimization problem. Where we want to minimize norm w square subject to the constraints that for all I, yi times w transpose xi plus b is greater than or equal to 1. Right. Now for this, we can write down the Lagrangian and solve for the KKT conditions. So the Lagrangian, which is a function of w, b, and the Lagrange multiplier. So we don't have any equality constraints, we only have inequality constraints. Right. So maybe before that, I should rewrite this in the so-called standard form. We want everything to be of the form fi of x less than or equal to 0. Right. So 1 minus yi times w transpose xi plus b should be less than or equal to 0. So I have n inequality constraints, one for each data point. So I need n Lagrange multipliers. So this is equal to norm w square plus summation I equal to 1 to n alpha I 1 minus yi times w transpose xi plus b. Right, and the KKT conditions would be the following. So firstly, all of the constraints should be satisfied. So we want 1 minus yi times w transpose xi plus b to be less than or equal to 0 for all I. And we have the complementary slackness conditions, which say that alpha I times 1 minus yi times w transpose xi plus b should be equal to 0 for all I, which means that either the constraint must be satisfied with equality or the corresponding Lagrange multiplier should be equal to 0. The third constraint is that the gradient should be equal to 0. Question? Question?
The labels y is are the -1.
They're all +1 -1.
If 0, it will be okay.
I'm sorry? If it's
0, then
it's impossible to get that. So we're assuming that henceforth we're going to assume that yi's are +1 and -1, at least in the context of linear classifiers and SVMs. In fact, we also did that when we talked about Rademacher complexities. Right? So almost always it's helpful to use +1 -1 as the labels. Okay. The third condition is that the gradient should be equal to 0. So gradient L of W B alpha should be equal to 0. Right? So what do we get when we take the gradient of this with respect to W? You get 2W plus summation I equal to 1 to n. We have alpha I times minus yi xi. Right? I'm only taking the gradient with respect to W, not with respect to B. This should be equal to 0. Right? So alpha I, so W is, if I take everything else to the right hand side, I get this is equal to half summation I equal to 1 to n yi alpha I xi. Right, so no matter what you do, the W that you ultimately get is just a linear combination of the data points. And moreover, just from the complementary slackness conditions, we know that not all of the alpha i's are going to be non-zero. It's equal to 0 if yi times w transpose xi plus b is not equal to 1. Right? Now we're guaranteed that yi times w transpose xi plus b is greater than or equal to 1. Right? So the points, if I sort of draw what we have, right? Let's say that this is what it looks like. Then the set of all points that satisfy yi times w transpose xi equal to 1, what points would those correspond to? So it would basically be those points that lie along these two lines. Okay. So it means that the W that defines the classifier is just a linear combination of those points that lie on these marginal hyperplanes. And intuitively, it's clear why it should depend only on those points that lie along the marginal hyperplanes. Because suppose that this is the solution to the SVM problem, or this is a max margin classifier, then if I delete any of these other points, right, or if I add any more points that are further away from the marginal hyperplane, then it should not really affect the solution of the SVM problem. It can't depend, the solution to the SVM cannot be dependent on any of the other points. Right? So these vectors that lie along those data points that lie on the marginal hyperplane, these are the support vectors. So one thing to note is that not all of these vectors need to be support vectors. By definition, the support vectors are those for which alpha I is not equal to 0 in the solution to the hard SVM problem. Right? And in principle, the set of support vectors is not unique, because this could be, let's say I remove some of these points, say I remove these 2 points, or let's say this particular point, the solution to the hard SVM problem still remains the same. All right? And the hyperplane, the marginal hyperplane still remains the same. So I should really say that these are candidate support vectors, in the sense that no other point can be a support vector, but some subset of these points are going to be support vectors. The solution to the hard SVM problem is going to be unique, but the set of support vectors is not necessarily unique. All right. If you try to compute the dual optimization problem, it gives a different interpretation of the same solution, right? I'm not going to do it right now, but the dual can be interpreted in the following way. You are given 2 sets of points. Remember that the optimization problem for hard SVM essentially tries to minimize this norm of W, which is not terribly intuitive, not directly intuitive. But the dual optimization problem turns out to have a more intuitive interpretation. So these are two sets of points that are given to you. The dual optimization problem, as it turns out, uh, happens to be you take the convex hull of these data points right. So these are two convex sets, polytopes in general, and the dual optimization problem asks for the minimum distance between these two convex sets. Or sometimes the way you formulate it, it's half of the minimum distance between these 2 points. Okay. And the solution is basically the solution to the primal optimization problem corresponds to a hyperplane that is a separating hyperplane for these two convex sets, and that separating hyperplane which is equidistant from the two convex sets. And the distance, the margin happens to be half of the minimum distance between these two convex sets. Questions? So in a similar vein, we can look at the Soft-SVM problem, which is minimize with respect to W, B, and Xi. Norm some lambda times norm W square plus 1 by n summation I equal to 1 to n Xi I, subject to the constraints that alpha I is greater than or psi I is greater than or equal to 0 for all I, and yi times W transpose xi plus b is greater than or equal to 1 minus xi I. Okay. Now, similarly, just as we did for the hard SVM problem, we can compute the Lagrangian and solve for the KKT conditions. And here again, we would expect something similar to happen. Essentially, W can only depend on those data points. W is again a linear combination of the data points, and it's a linear combination of only those data points which actually determines the separating hyperplane, right? And In particular, it can only depend on those. So firstly, it can depend on those points which kind of define the marginal hyperplane. And it can also depend on those points which are so-called outliers. Right? You can classify those points. You can look at the collection of data points that you are given, and some of them are going to be outliers, those which cause errors, which are sort of far away, and those which lie on the marginal hyperplane. That is, among the correctly classified points, those points that are, so this is what is given to you. These would be the marginal hyperplanes. So the support vectors can only come from these vectors or these outlier vectors. All right. It does not depend on any of the other data points. Question? So, yeah, whatever. The alpha i's are not necessarily the Lagrange multipliers in this context. It's some linear combination of the xi's.
What is Kali? Kali is it the error?
So this basically tells you the error, right? So if the points are correctly classified, then this xi is equal to 0. But if it is not, then it tells you how far away is it from being in the correct side. Right? It's a measure of this particular distance. Right? Yeah, or to be more precise, it's proportional to this distance. Right? Similarly, for this point, it would be proportional to this distance. The distance of the incorrectly classified point from the corresponding marginal hyperplane. Okay. So this soft SVM optimization problem, it can also be written in a different form, which gives another interpretation to this optimization problem. So this is equivalent to minimizing with respect to W and B lambda times norm W square plus some function it's an unconstrained optimization problem. And what is this RS hinge? it's an empirical risk, but the risk is not with respect to the 0-1 loss, but instead it's the empirical risk with respect to the so-called hinge loss. So this is equal to summation 1 by n, summation I equal to 1 to n of max between 0 and 1 minus yi times w transpose xi plus b. Right, and now suppose that this w transpose xi, suppose that this were replaced with, if you considered max between 0 and 1 minus yi hat, right, where yi hat is either plus 1 or minus 1, and yi is also plus 1 or minus 1, then what would this be equal to? 0 or 0 or 2, right? So more generally, so you can see that at least when you take w transpose xi plus b to be equal to 0 or 1, then you see that this is greater than or equal to the 0-1 loss. We can also plot this. Minus 1. The 0-1 loss would look something like this. Right, so this is, say, indicator yi times w transpose xi plus b greater than or equal to 0. Sorry, this is, I should say, let's see this, if I say sine sine of x less than 0. Less than or equal to 0. Right? So when we use the classifier, let's take x to be equal to 1 minus yi times w transpose xi plus b. Right? So if so, h of x is basically the sine of w transpose x plus b, and the 0-1 loss is indicator of y times w transpose x plus b less than 0. Right? If both y and w transpose x plus b have the same sign, then you classified it correctly. If they're of opposite sign, then you classified them incorrectly. Right? So I can replace this with, let's say, some other variable, maybe u. So this is indicator u less than or equal to 0. And I can also plot the following hinge loss, which is max of 0, 1 minus u. What would this look like? For u greater than 1, what is it equal to? It's equal to 0, right? So it's equal to 0 for u greater than 1. And what happens for u less than 1? It's equal to 1 minus u. So it looks like this. So for all, no matter what happens, the hinge loss is always an upper bound on the 0-1 loss. Right, so if this is the 0-1 loss, y comma h of x is always greater than or equal to the 0-1 loss between y and h of x, no matter which predictor you use, right? In particular for linear classifiers, right? So this means that if I am able to sort of derive a generalization bound for the hinge loss, then I can also derive a generalization bound for the 0-1 loss, because the 0-1 loss can only be less than the hinge loss. So coming back to this particular equivalence, I said that soft SVM is equivalent to minimizing the following objective function. Right? It's an unconstrained optimization problem, but this is also equal to, so this particular quantity, right, this particular minimization problem, this can be viewed as again an empirical risk minimization problem with an L2 regularization term. All right. The empirical risk minimization is not taken with respect to the 0-1 loss, but rather with respect to the hinge loss. But you're not just doing plain empirical risk minimization. There's also another factor, a regularization term, which is just the L2 norm.
Why do they call that regularization?
Anything which, so if you have any objective function, right, so you minimize some function f of x plus some constant, typically something like a hyperparameter g of x. This can be viewed as your ultimate goal is to actually minimize f of x, but you have some plus lambda times g of x in order to bias your solutions in certain ways. All right, so this is So instead of just minimizing f of x, you minimize some linear combination of the actual objective that you're interested in plus some regularization term, such that hoping that this regularization term will bias the solutions in a certain way. Maybe the regularization term encodes some property of the constraints that you have.
So in that case, constraint is it like norm of W is equal to 1 W?
Not really. Basically, what you want to do is bias the solution towards those for which W has small L2 norm. Again, if you go back to the soft SVM problem, we were actually minimizing W, the L2 norm square of W, right? Here, again, it's an interpretation, right? The interpretation is that you minimize the hinge loss, but you also have a regularization term. But this also has a deeper reason, and the deeper reason is that, as I said, you want to derive a bound on the generalization error, right, corresponding to the 0-1 loss. What you can instead do is derive bounds on the generalization error with respect to the hinge loss, with this as a regularization parameter. Now, there are ways to derive bounds on the generalization error when you have an L2 regularizer. We'll maybe see that a little later in the course. But using this, viewing this as ERM with L2 regularization, you can derive bounds on the generalization error with respect to the hinge loss. And because you have a bound on the generalization error with respect to the hinge loss, you also almost for free get a bound on the generalization error with respect to the 0-1 loss.
So we also saw that there are infinite possible W's in the linear classification. You can choose W's, you can simply scale them and we get a new solution. So here we are saying that we also bring W also down, along with minimizing volume.
Well, okay, so that there's it's a little subtle over there. When of course, when I said that there are infinitely many W's, there were two reasons initially. One was that if I scale W and B by the same amount, it doesn't change the solution. Therefore, there are infinitely many W's. So in that sense, this is trying to minimize, this regularization term is trying to take care of that. But up to this scaling factor, the solution of hard SVM or soft SVM is unique because the hyperplane is still the same. If up to the scaling factor of both W and B by the same amount, right? Because initially, if we didn't have this margin constraints, if we didn't want a max margin classifier, then in fact, that if you take, let's say, the case where the data set is linearly separable, it was not just that the solution is not unique up to scaling, it's not unique at all because there could be infinitely many hyperplanes that correctly separate the data set. Right. Any other questions? Okay. So now let's again take a look at the soft SVM optimization problem. The goal is we basically have a quadratic optimization problem with a bunch of constraints. And one way of obtaining a solution to this is you just plug it into some solver and then try to get the solution, right? Which is fine. Because the solver takes polynomial time. The problem that you will eventually encounter is that the complexity of the solver will ultimately depend on the number of variables and the number of constraints, right? So all of this is fine if the dimension of X and the number of constraints is reasonably, it could be large because modern solvers are pretty good, but for moderately large sizes everything is fine. Let's say a few thousands up to maybe even 1,000,000 points or so, everything is fine. But then you'll start running into trouble if the number of points is massive, which is what we have in most modern data sets. Right? Then what do? You can't obviously get a solution to this Soft-SVM directly, but instead what you'd want to do is try to solve the minimization approximately using some kind of an iterative approach. And one iterative approach is to use stochastic gradient descent. And in particular, you run stochastic gradient descent for this particular optimization problem. Minimize W, B with respect for this objective function. Okay. The advantage of this particular formulation is that there are no constraints. So it's an unconstrained optimization problem. The disadvantage of, or the small bottleneck that you may run into is that this is not a differentiable function, because the hinge loss, as we've seen, it's not differentiable at this particular point.
It is subgradient.
Exactly. So we'll use subgradient methods. Okay. So let's discuss gradient descent and subgradient descent and stochastic gradient descent in a little bit of detail, in slightly more generality. So maybe even before we move that, let me make a couple of points. So this, remember, our goal was to design a classifier, a good classifier, and we started out with a max margin classifier, right? For hard SVM, everything was fine. But when the data set was not linearly separable, it turns out that computing the empirical risk minimizer is hard. Okay? So we came up with this approximate solution. It's not an optimal solution, but maybe a suboptimal solution. And the suboptimal solution was Soft-SVM. The way I introduced Soft-SVM was a sort of a tweak to the hard SVM problem. That's one way of interpreting Soft-SVM. The other way of interpreting Soft-SVM is, as I said, instead of trying to do empirical risk minimization over the 0-1 loss, you do empirical risk minimization with respect to the hinge loss with a regularizer. And this sort of approach is what is most frequently used in most machine learning problems. You want to actually minimize, actually want to do empirical risk minimization with respect to some loss, but for whatever reason, it's too complicated. You don't have a computationally efficient solution. So one approach is to replace the loss that you're interested in with a surrogate loss, something that is nicer and easier to work with. All right. In this case, the surrogate loss is the hinge loss. And potentially to make your objective function a little more smoother, or to bias the solutions towards certain well-behaved solutions, we also add a regularizer. One of the most frequently used regularizers is the L2 regularizer. All right. Sometimes for other problems, you may want to use an L1 regularizer. Let's say you want to bias yourself towards sparse solutions and so on. There are deeper theories behind why you would want to use certain regularizers and when you would want to use certain regularizers. We'll see a little bit of that later in the course. But this is the trend that you will see in most machine learning problems. All right. So that's one approximation, right? You wanted to solve empirical risk minimization. We know what guarantees we can get if we do empirical risk minimization with respect to 0-1 loss. We got generalization error bounds. But in practice, you can't do that. So the first thing is you approximate the objective function. You use a different surrogate function. The second approximation that you use is you don't even minimize this, you don't even solve for this surrogate objective optimization problem exactly. You're happy with an approximate solution. Because in this nice case, this happens to be convex. The objective function happens to be convex and everything is good. But in practice, even by replacing a surrogate function, you don't end up with a convex optimization problem. In general, if you try to look for a surrogate function where everything is convex, you will not get good performance. So you still don't mind the fact that the objective function could be non-convex, but instead you try to solve for this optimization problem using an approximate iterative method, something like gradient descent, or to reduce complexity further using stochastic gradient descent. All right. So for the rest of this discussion, we'll assume that we have some objective function f from, let's say, Rd to R. This is convex. And at least for the first part, we'll assume that it's smooth, so the gradient exists.
How do I know that the gradient descent gives an approximate solution for that? Did you discuss it in any of the previous classes?
Why gradient descent gives an approximate? So that's what I want to say here, right? So we'll assume. So firstly, I hope it's okay that this objective function is convex. Right? That's okay. So right now we are given some objective function, not necessarily the one that is before, that's provided earlier, but it's some convex convex function, and the goal is to minimize this convex function, or at least get a solution that is epsilon close to the minimum. All right. So gradient descent would start with some initial point x0 and then perform the following sequence of steps. Let me denote this x0 and then for a certain number of steps you take x t plus 1 to be equal to xt maybe 0, 1, so on, xt minus some delta times, let me use eta, perhaps, gradient f of xt. So this is the standard gradient descent procedure. You can potentially also use this if the function is not convex. Right? At least the algorithm remains valid. What guarantees you can get are totally different. Okay. What we want to know is after, let's say, t steps, how close is this to the actual minimum? Okay. Of course, we can't say this for arbitrary functions and for arbitrary initial points. You need some kind of assumptions as to how far you begin with and how smooth your function is. Okay. Sorry?
Is at least beta from the...
Right. So it's at most some distance b from the start, from the minimum point. So assume that x star is the minimizer for f of x, we will assume that the norm, the distance between x0 and x star is at most some quantity b, and we'll also assume that the gradient is bounded. It's less than or equal to rho. Okay. So basically the gradients can't blow up and therefore take you too far away in every step. Okay. And for now we'll also assume that the step size, or what is also called referred to as the learning rate, is kept fixed. We are free to choose it depending on these parameters b and rho, but is otherwise fixed. You're not going to change it per iteration. In practice, this is not what is done. In practice, many of these assumptions don't hold. Convexity doesn't hold. The property that you're sufficiently close to the objective doesn't hold. All of these doesn't hold. That requires a separate theory of its own. But it's still good enough to explain many machine learning problems or many optimization problems. Okay, so these are the assumptions that we have, and using this we want to analyze the behavior of gradient descent. Now, I won't give a full proof, but I guess we've seen this to some extent in the convex optimization course, but I'll just outline some of the main steps that were used to derive a bound on how gradient descent performs after t steps. Okay, so typically in the analysis, you make a small modification, that is, at the end of t steps, you don't see how far xt is from x star, but rather the output of gradient descent is x bar, which is the average of the iterates. Okay. This is generally done for analysis. It just makes it easier to analyze this. Okay. And you can immediately see why this is easier to analyze. So if you look at f of x bar minus f of x star, this is less than or, note that x bar is 1 by t summation t equal to 1 to t xt, right? So it's an average of some vectors, which can also be interpreted as an expectation of a random vector with respect to a uniform distribution. So using Jensen's inequality, this is less than or equal to 1 by t summation little t equal to 1 to capital T f of xt minus f of x star. This just uses Jensen's inequality, right? So this is 1 by t summation t equal to 1 to capital T f of xt minus f of x star, and using the first order property of convex functions, remember that f of x is always going to be, so if you take any convex function, the convex function is always lower bounded by the tangent hyperplane passing through any of the corresponding, any point that passes through the function. Right, so this is less than or equal to 1 over t, summation t equal to 1 to capital T, gradient f of xt times xt minus x star. Now, here's a result that I will not prove, which where really most of the analysis lies. It's nothing significantly complicated, it's just algebraic manipulation. It says that if you have any iterative algorithm where you have iterates of the form xt is equal to x t minus 1 minus some eta vt. Question? Question? Right? So if you have any algorithm which takes this particular form, then you can write summation t equal to 1 to capital T xt minus x star in a product with vt to be less than or equal to norm x star divided by 2 times eta plus eta by 2 equal to 1 to t norm vt square. So basically the sum of the inner products is at most some quantity that is bounded by x star. So x star is a for any arbitrary x star. So Vt doesn't necessarily have to be the gradient, and x star doesn't necessarily have to be the minimum. It's a fairly general result. So from our assumptions, so if we just apply this lemma, we would get f of x bar minus f of x star to be less than or equal to 1 over t times x star by 2 eta plus eta by 2 times summation t equal to 1 to capital T norm Vt square. So that's norm gradient f of xt square. Yes.
When you approximate the gradient, can you explain?
Yeah.
Here, shouldn't it be x star minus xt? That is most part.
So f of x star is greater than or equal to xt, x star should be greater than or equal to f of xt. Yes, that's correct. Correct. Yeah.
We did a side mistake, yeah, sister. It should be xt minus
So f of x star is greater than or equal to f of xt. Yeah, correct. So it's xt minus x star itself. F of x star is greater than or equal to f of xt plus gradient of f of xt times x star minus xt. You take f of x star on the other side and the other term, the gradient on the other side. So it's, this is correct. Right? Okay. So now this quantity is less than or equal to 1 over t times, we'll make another assumption that the norm of x star is also less than or equal to b. So if we do so, this is less than or equal to b by 2 times eta plus eta by 2 times t times rho. Right? So if we choose eta equal to b divided by rho times square root of t, then this is less than or equal to rho b times rho divided by square root of t. All right. So this required some strong assumptions, particularly on the points that you were considering, the solution, as well as the the solution as well as the gradients. All right. But many of these can also be replaced. So instead of looking at the norm of the gradient, you could also say that the gradient is sufficiently smooth, or correspondingly that the function is Lipschitz. Right. So function.
Should that mean that
Yeah.
a norm of x stars, should that be a square? Square and it should be rho square as well. Then you get eta.
Yeah, I think I wrote this wrongly. So I think this would be b square. So I get b. Correct. So this would be rho square. Correct. So eta is indeed the learning rate or the step size.
Usually choose the learning rate, but can we make an assumption like let eta be is that fine?
So if you choose the learning rate in this particular way, this is the convergence rate that you can guarantee. For something else, so typically when you're trying to do an analysis of gradient descent, you fix the learning rate, assuming that, so this is the best choice of learning rate you can get. If you choose it to be something else, or you choose a different step size, then it is going to get worse. All right. But in practice, you don't have this luxury. You typically don't know what is the value of b or rho. Right. So you can also replace this with the Lipschitz constraints. So f is I say rho Lipschitz, it means that norm f of x minus f of x prime is less than or equal to rho times x minus x prime. It turns out that these two are equivalent, so in a sense we are saying that the function is sufficiently smooth. So one point is that in all of this analysis, I didn't actually have to use gradients. I could have as well replaced these with subgradients. What is a subgradient? So if f is convex, right, then for all x, then for every x there is some vector v that can potentially depend on x such that f of x prime is greater than or equal to f of x plus vx transpose x minus x prime. So in other words, if f is convex, then at every point, if you take the curve, there exists a tangent which uniformly lower bounds the entire function f. Okay? And that's true even if the function is not convex. It is just that at the points where even if the function is not differentiable. So if the function is not differentiable at a particular point, then Vx may not be unique. So Vx is called the subgradient. It's called a subgradient of f at x. So Vx may not be unique. So for any x, this is the set of subgradients at x. In particular, Vx or the subgradient is unique only if it is differentiable at that particular point. So in that case, the gradient is equal to the subgradient. So if the function is differentiable at all points, if it's then the set, then every point has a unique subgradient that's equal to the gradient. So all of this analysis that we did earlier for gradient descent can also be done for subgradient descent. In fact, I didn't really need the function to be differentiable at all points. The only place where I used the gradient, brought in the gradient, was this step. And this step also holds if I replace the gradient with the subgradient. This particular lemma didn't really care what Vt was. So I could replace this with the subgradient. And all of the remaining analysis goes through as long as the subgradients are bounded by rho. That's it.
A few slides back, we had a term where we average all inputs.
Correct. So basically, my x bar was this, right? We assume that the output of gradient descent is this. It's the average of all of the terms.
Average
Of all of the xt's.
okay, because we told that linear combination of all those supported
No. Not necessarily. So the xt's don't. Okay. Maybe you're getting confused a little bit with the notation. The xt's here have nothing to do with the data points, right? At this point, right now, we're looking at optimizing an arbitrary objective function which is convex and has some nice smoothness properties. That's it. You can forget about SVM and everything else that we did before that.
But why are we taking average here?
We are taking the average just because it makes the analysis of gradient descent easier.
And we are not using that.
We are, right? F of x bar is less than or equal to this. So it's purely for this particular step that we are using. So suppose I, instead of taking x bar, I just took xt. Okay. Then effectively f of xt minus f of x star would be equal to just this term without the summation and 1 over t. Alright? Which means I can't really invoke this particular lemma in its form. Alright? So it's just a proof technique, nothing else. In practice, you would not really take the average.
Which would imply that in practice we would always get much worse time counting.
Not necessarily.
Since we are taking just
No, not really. Because you start out with something that is really far away, right? So, I mean, if you think about gradient descent, in fact, this is worse than taking just xt, because gradient descent is guaranteed to get closer if the function is sufficiently smooth. Then at every step you're always reducing the objective, which means that you're getting closer to the minimum at every step. So if you take xt versus xt plus 1 plus xt plus 2, everything divided by t, the average is going to be farther away from the minimum than xt. So whatever you get at the end of this analysis is a more pessimistic bound than what you can actually see in practice. But it's just that it makes analysis easy. That's it. Under these assumptions, of course. Okay. All right. So all of these bounds that we have hold true even if I used subgradients instead of gradients. Question?
Can the set of subgradients be zero at turning point?
No.
Or an empty set?
It can't be the empty set if the function is convex, right? Because by definition, I mean, this I agree, it's a property of convex sets, right? For every x there exists at least one Vx such that this holds. And in fact, any function such that this property holds for every x is convex. So it's an equivalent condition for convexity. So in fact, something similar holds even if I replace the subgradient or the gradient with a random vector which is equal to the gradient or subgradient in expectation. So stochastic gradient is a random vector v such that expectation of v, so it's a vector that depends on a point x, expectation with respect to vx lies in the set of subgradients. So in particular, if it's a differentiable function, then in expectation, this stochastic gradient is equal to the gradient at that particular point. So this source of randomness comes somehow from the algorithm. We won't worry about where this source of randomness comes from. But all of the randomness is independent of x and everything else in the rest of anything to do with the function. And SGD is exactly this. Instead of using the gradients, so now it's a randomized algorithm where at each step you take xt equal to xt minus 1 minus some eta times v xt minus 1, right, where this is a stochastic gradient. So now it's a randomized algorithm. You can't really guarantee that you will actually satisfy. So you can't say that with probability 1, these bounds hold true. All right. But as it turns out, if you can show that if all of these constraints are still satisfied, that is the norm of the stochastic gradient is bounded, and you start from a point that is, so if norm Vx is less than rho with probability 1 and x0 minus x star is less than or equal to b, and I run stochastic gradient descent and again take the average of the xt's, then the expectation of f of x bar minus f of x star, you can show that this is still less than or equal to b times rho divided by square root of t, where again I chose the step size eta to be the same, b divided by rho times square root of t. So this is the random vector, right? That's the stochastic gradient at the point x. So it is defined to be a stochastic gradient at the point x if the expectation of this particular vector is a subgradient at x.
What is the notation? Delta.
So remember that the subgradient is not unique, right? So this dou f of x is the set of all possible subgradients at the point x. So in expectation, the stochastic gradient must equal to one of the subgradients. Any one of the subgradients is okay. If there are multiple subgradients, if the function is differentiable at that particular point, then you want the stochastic gradient expectation to be equal to that of the gradient. Any other? Expectation is with respect to, so there is some randomness in the choice of this random vector. Expectation is with respect to that randomness. So maybe this is a good point to stop. So we'll see where stochastic gradients come from, and SGD for learning problems, in particular for empirical risk minimization, how it reduces the complexity, and therefore what can we say about the runtime of stochastic gradient descent for empirical risk minimization.